as I was saying, I have been researching the Atacama Desert for a long time now, and the Atacama is well known because it's the most arid and also oldest desert on Earth. And I have been studying this fascinating place, trying to understand the close relationship between water and life, and that what can that tell us on how we look for life elsewhere, Mars in particular. So in time, I have found places like this one. This is a cliff just confronting the Pacific Ocean in the coastal range of Atacama, in which we have found a few places where microbial life is able to survive exposed to the environment. That is the epilitic way of life, because there the ocean means provides enough water for life, as I said, to be exposed in such extreme environment and where you not only have a very dry air, but also huge UV radiation. Also in the coastal range, we have found, for example, different type of habitat, in this case, caves, and we have found even photosynthetic life at the very bottom of those caves, in which you receive less than 0.01% of the amount of light you have outside. In other caves, where just a few meters inland in the coastal range, we have similar but at the time different phenomena. In this case, we found photosynthetic life going not on top of the caves, but on the web, the spider web that are attached to the cave entrance, because there, given that the spider web is highly hygroscopic, you find this new type of the only actual member of the Dunaliella genus that is able to survive in a superbarium environment, because these guys learn that in order to get a source of water, it would be a good idea to grow on top of the spider web. Then if you move just a couple of hundred meters into the coastal range, you find this phenomena in which you find microbial life below rocks, that is the hypolytic way of life, because there light is able to traverse the quartzes, and then because quartzes keep colder than the environment, you're able to find at least 80 different type of species below these quartzes, being actually true representative of islands of biodiversity, having found there bacteria of all types, archaea, and also eukaryotic members like fungi and also microalgae. Then we go into the true hyperadic core of Atacama, in places where we have and others measure that typically after midday, relative humidity drop to zero. That is how dry those sites are. But amazingly, in these places, and here I'm showing you the driest place on Earth, where you have again the very same phenomena. You have to dig into the soil in order to find life, but amazingly, up to a meter or more of depth, we have found a few microorganisms living there, and we're trying to understand how they're able to do there when you have water activity around only at the most of 0.15. Okay. Just to give you an example of how these species are so well adapted to the environment, this happened in 2015, 17, and 19, that great masses of air came from the Pacific Ocean and started making these rain lagoons that no one has ever seen them in these places. And that's because due to global warming, the temperatures of the water of the Pacific are getting higher, thus getting more evaporation, then more clouds, and then rains that coming from a direction that had never been recorded in the climatic history of Chile. So you would think that this input of water would mean a plethora of life coming from the soil that have not seen water in some cases for millions of years. But contrary to our expectation, we found that these microorganisms are so well adapted to the low amount of water that when you give them too much and too soon, they simply get all the water inside as much as they can and just burst and disperse their content around. This is an example of how well they adapted, because we were able only to measure the biosignature left behind by such microorganisms. So in time, I have seen how life in the Atacama, when you have enough water, like in the Cofa Cliff, where water activity goes between 0.7 and 0.9, you can yet still in a few the privileged spot, and you can see microbial life growing exposed environment. You just go a few meters inland, you have to find a shelter, in this case, under a rock. Then somewhere in that area also we have found similar phenomena where you have to get into rocks, the so-called endolitic way of life. But if you go underground, I mean, if you go inland in the hyperbaric cold, you simply have to dig yourself into the ground to survive. As a general lesson on how life is able to adapt to such extreme environment. So as you may say, this is a very interesting trend, because this is the very same trend you will have expected to happen on Mars when it had more water, and when in turn Mars starts getting drier and colder. That's what you would expect to find life now in the underground, not nowhere else. And considering that the environment on Mars is much harsher than the one you can have on the Atacama, right? Well, the other way to see it is, well, let me know what epoch of Mars you're interested in understanding. I will tell you to the precise place of the Atacama where you should look for evidence of life, the type of life, where you find them, in order to understand how Mars evolved in time. Of course, all these have been published. So you just look for my name in ResearchGate, where I have all this is all these reports. But there was one missing yet factor of analogy that I was looking for, in order to tell what this is actually as Martian as you can get. So as I said, the hyperaric core is characterized by extreme aridity, the extreme UV radiation, but the one thing I was looking for is what the typically reddish color that I have not seen before. So when in around 2016, NASA released these images of Mars, it hit me that I have seen this place before. And that's because in the way we go into the Atacama, we usually pass this place, which is redstone. And here, just note that I have changed just the color of the sky to tell you how reddish it is. And our preliminary exams told us that that is a place that you could find hematite, the same iron oxide you would find on Mars. So then we start characterizing this site. We explored it really well in order to understand what this actually site was telling us. First, it was very interesting to see this succession of sediment between sandstone, mudstones, and different type of evaporite, mainly salt, the common sodium chloride, and also gypsum, forming different type of configuration that tied to the geological history of the area. We knew that this was part of a very ancient part of the Atacama from the Jurassic, that is between 160 and 100 million years old. So it was a very old site. And also that this was the remnant of an ancient alluvial fan, which point of origin 9 is now under the Pacific Ocean, which formed under added conditions. And we know that because of all the presence of evaporite. Okay. And as I said, looking at the geology and the mineralogy of the site, we found hematite being a component everywhere. And the site looks really reddish because you don't only have the hematite crystals, the H's that the H letter you find there, but also that the dust of the hematite as a coating was covering everything else. That's why everything looks so reddish. Then we start characterizing, well, now we have another factor of analogy beyond all those, plus hematite now. Let's see what is the habitability of the place. Here, as you can see, no plants and anything, just as rock as you can see them. So we found a number of different types of microorganisms of different families we knew, but it called our attention that 9% of our sequences went into the category of unclassified. So that's what was intriguing. So we reordered all our data again in order to see, well, how much information do we get per sequence. So here you can see that only 2% of the sequences you could get to the species name. Let's say Bacillus subtilis. Okay, in 50% of the cases we could get to the genus level. That is, well, okay. So we have now a species of Bacillus, but look at all of the one in gray color there, all that are in the higher categories, with the most striking example that more than 15% of the sequences could only tell us a domain. So, okay, now you have a sequence, you compare it with a database, and the database tells you, oh, I just know that you have a bacteria. That's it. I cannot tell you more, no more than that. So actually, if you add those, and then the unclassified, and if that didn't even go into this spike here, you almost have 50% of the sequences with little information. And with that, we baptize a new term based on what our fellows astrophysicists have found in the universe and dark matter. We said maybe this is a place we have discovered a dark microbiome. That we know that microbial species are there. We have even their 16S or 18S sequences, but we cannot classify them. This is one of those actual sequences. If you compare with different databases, you will have a tag like this one, unknown, unclassified. I mean, how many ants can a term have? Okay, so now that we knew that from extracting DNA from the soil, we have that response. Well, how many of this bag could we grow? And let me tell you, we have a pretty good experience of trying to grow things from soils like this one. And the usual response is that you have to wait several weeks and use many hundreds of plates to, for example, in this case, just get one colony of something that you could grow. But when you can grow it, you could also extract enough DNA, and from DNA you can identify it. It's a species like this one. So what we found here, for example, bacillus. We have seen bacillus all around Atacama. No surprise here. Halobacillus is interesting because this is the type of species you will find typically associated, and you can guess for the name in saline environment. And guess what? We found it in the halite samples. Same thing, same applied for Bacillus, very similar in habitat selection for Halobacillus. Blastococcus also is interesting because Blastococcus, after Deinococcus, is the one that it has shown to be truly tolerant to huge amount of UV radiation. A fungi that we could even tell the genus, say, well, we have a fungi here. That's what we can tell. Not even go into the genus because the family and the genus here is so unresolved that people that is not have yet reached an agreement on how to call things there. And just one other fungi, not easy to find again, which the one of the few species we actually get from the eukaryotic point of view, we will give it at least give it a genus. We could see by staining the sample DNA, by watching many after field, a few colonies here and there. That's it, no more than that. Typically, when you find this type of colonies, when you find this halo that is difficult to see here, but it's there. Maybe they are because maybe they may be collaborating in order to survive such extreme environment. And when we check the lipid biosignatures in order to say, well, what a robot would see as evidence of life, note that the total organic carbon content is really low, from 0.02 to 0.1. That's the highest values, which explains that most of the molecules we were looking for were not detectable. But there was a pair in just a few of the samples, which is pristine and phytane. And pristine and phytane are interesting along hopanes, which are the most recalcitrant lipid biosignatures you can find around, because these two molecules are the remnants of chlorophyll along hopanes that are the very long remnants of lipid membrane. And given that we knew that we have mudstones, a mudstone compared, let me give you the little here, clays like vermiculite and smectite and chlorite, etc. And given that we didn't have any other evidences of photosynthetic organisms, neither for microscopy or DNA or whatever, we think that we're actually seeing here are the remnants of the species that inhabited this site when it had water millions of years ago, which you could only evidence were the degradation process of chlorophyll, which is, by the way, explain why rovers like Perseverance have been sent to places with clay in order to find evidence of life, as we have seen here. I mean, the only evidence of life on an entire ecosystem here, in our case, would be, for example, the remnant of chlorophyll. That's it. So once we have characterized our site, the question would follow, well, let's bring actual detection instrument to the place. What those instruments would see now that we have singular, so to speak, ground instrument just about the level of the detectability, and whatever we can detect, they are quite strange. So the question is, instrument of like this, what would they see? So we started with some like pyrolysis on board the Curiosity rover, in which samples are able to be taken into the rover in order to be analyzed. For example, Sam was able to see some aromatics, but not in all samples. Then some alkanes barely at the limit of detection, but again, not in all samples. Alkanes were detected, but not detectable by the flying instrument because the instrument we were using was 10 times more sensitive than the one that is on Mars now. However, after derivatization, a few carboxylic acid, other molecules, and also proline were able to be detected, but again, not in all samples. And also that the carboxylics and unsaturated fatty acids would only have been detected on Mars if they were abundant enough, because again, here it was just about the level of detectability. In the case of MoMA, the Mars Organic Molecular Analyzer, which will be on board the Rosalind Franklin rover, they directly could not detect organic, but after derivatization, it was able to detect aliphatic carboxylic acid, but only one sample. The solid L chip, an instrument that we created here in our own institution that is able to use a panel of antibodies to detect different type of critical biomolecule for all life novel, just a few hits, just over the detection minute, but at least in all samples. And interestingly, it was able to find evidence of fucosylate subinucleic alpha, which is one of the antenna pigment and cyanobacteria uses. There, as I'm showing here, that is immersed water. Actually, this is one of my pictures of my own cyanobacteria where all the photosystems are located. And then why that is interesting? Because that supports our hypothesis that again, we have evidences of the ancient environment that this had when it had water a lot, many millions of years ago. And finally, diffuse reflected infrared Fourier transform spectroscopy was also barely detect organic, but just in the near infrared region, and just a few very weak bands in the mid infrared region. So all this was published, so you can get all the data itself in the publication. But as you can imagine, with this report, I met a lot of new friends, right? Because I was saying, well, we have to do a better job. But for me, it's the way the science works, because first, it let us know on the importance of Mars analog model. These are not just play tools for us to work. Actually, they give us really nice information, right? Because we're now, for example, thinking about sending a return mission in order to bring my samples on Mars. But let's not forget, in my case, given we have sought now, that all the samples that the Perseverance rover is collecting are surface samples along the same samples, not more than 30 centimeters of depth that were taken by the Viking mission. But there is one thing that I learned in the Atacama is that the surface soils are so extreme in terms of temperature changes, UV radiation, salinity, etc., that they are almost close to sterility, and you have to go deep into the soils in such places in order to find just a few bacteria. I have been trying to find lately some biosignatures in this soil. It has been impossible. So now to tell that if you bring samples of Mars, because they are too superficial, maybe you will not find anything. Probably I will make even more new friends. But there's some hope, because the MoMA will go into samples as deep as we have looked in the harshest parts of the Atacama, that is 1 meter of depth. So there is a chance that actually this guy is going to detect things that the others would not be, because they are going in the proper place, which is the surface of Mars, in time of all the findings. But let me finish with just one comment here. Let's imagine we are on Mars and we found a pot of organics as huge as you can find in the Ryugu asteroid, in which all type of organics were found. Everything you would look for, not all everything, but almost everything you would look for we was found there. Has anyone claimed that they have found evidence of life on Ryugu? No. So let's put all the semos organic on the surface of Mars. Could we say that with evidence of life, we have found evidence of life on Mars? No, we don't know. We could be coming from such bodies that we know there are a lot because of most of all the impact craters that are there, right? So why would you look for evidence of life instead, from my point of view? First, give me polymers. If I were to find something like an amino acid chain on 10 or more, and ideally chains that differ in amino acid composition, that would be a pretty good evidence of life for me. Or sugars for the same reason. Give me a long, and then a variety of long chains of sugar, that would be also nice. Second, morphological internal complexity, because what you are seeing here, they are all pseudofossils, fossils that have been created on purpose that have nothing to do with life. But I haven't heard about looking at morphological internal complexity, because that if you cut one of those things and you have a complexity like this one, or like this one you can see here, that are actually true, one of the oldest recognized fossils, that is very difficult to create without life being intervening. So morphological internal complexity. And the third one actually is, we have been testing a software based on fractal mathematics and artificial intelligence that actually is able to tell us that, because we use this, for example, the software in this image here. You can see here a rock covered by lichen, and ask the software, can you interpret that orange thing is actually a lichen and it's not a part of the rock? And our software was able to actually do that, separate all the data and say, yes, I can measure that by using fractal mathematics, that whatever that is, the orange thing is, it has a higher structural complexity, thus I can separate it from the rock, and thus go there and inspect it, because it may be made by life. Same thing when analyzing from the point of view of an orbiter. For example, these, we know there are bands of plants. Can we, from a space, tell that this band of plants differ from different banding of just pure geological reason? Origin, yes, that software also can tell you, oh, there is a difference there in how these bands are made, and that can tell you that some of them are more complex than others. When we input a sedimentary pattern taken by our orbiter on Mars, the response was intriguing because it was just in the middle. If we compare banding pattern of non-biological origin layers with purely geological ones, and if we put this data inside, it just went into the middle, adding to the question that Mark also is posing us, that is difficult to say. That say, well, maybe, and given that we know that sedimentations are so altered when you have life, that maybe this sedimentary pattern may have been being touched by life at some point or another. And finally, and with this I think I end, the one thing we tend to forget, that this phrase was not said by Galilei, but it's still attached to him. Anyway, it moves because many microorganisms move. And we tend to forget this. So if we were to keep, for example, to have a graph of the water that we suspect that is seeping in some of the crater walls during summer, and then inspect that water as a representative of a bigger amount of water that is in the underground, if I see something swimming, and there is no way you can interpret that as something that is living, right? And so with this I end. Just give you a last example. For example, we found this thing under one of the quartzes that are not colonized in the hyperarch color of the gamma. We have no idea what is it. We haven't been extracted DNA because we will find one or two per quartz, per 100 quartz, which are not enough to get DNA or anything. Yeah, we just know there is something that is transparent, that it seems to be bigger than a bacteria, but smaller than a eukaryotic cell, and there are things moving around. We have no idea what is it. That's the kind of thing we need to resolve when we go to Mars. And with that, I end up, and I will welcome all questions and doubts you may have on what I just said. Thank you very much.